Now, of course, integration is not merely doing educated guesses. We have also some basic rules. Now, we'll illustrate these rules by a few simple examples. So let us suppose that we have a function little f of x and we want to compute the primitive, or a primitive at least. Now, what happens if you take derivatives when you have such a polynomial, then the power goes down by 1. So if we integrate, since integration is anti-differentiation, the power has to go up by 1. So we should get something with x squared. Of course, if we take the derivative of x squared, you get a factor 2 in front. We have 3, so we have to multiply by 3 over 2. Now, if we look at the collection of all primitives of the function 3x, then we have this one particular function, 3 over 2x squared, plus an arbitrary constant. The second function that I would like to consider is g of x equal to x squared. Now again, the same reasoning applies. So if we integrate, then we have to, if we integrate this function, then we should get something with power 3, because the power goes up by 1. So let us write this primitive by capital G. It should have a factor x to the power 3. If we differentiate, we get a factor 3 in front. We have a factor 1, so we have to multiply by 1 over 3, and then we get the right thing. Of course, if we list the collection of all primitives, then we get this one primitive, 1 over 3 multiplied by x to the power 3, plus an arbitrary constant c. Now, the rules that I'd like to mention here are listed in Theorem 3 of section 5.4. And the first one is that the integral from a to a, so if we in fact integrate over one point only, then we get 0. Now, why does this make sense? So let us draw this function. We have a special point, little a. The integral is equal to the surface of over this line, because we have a function that is non-negative here, so the integral means simply the area. Under the function, and well, the area of a line is 0. Okay. Now the second rule is that if we change the order of integration, then the result is minus the original integral. The third, this is the one that we will apply most. So if we multiply our function little f by a constant f and add a function little g of x multiplied by a constant b, we compute the integral from a to b of this function. Then we might as well calculate the integral from a to b of our function little f of x multiplied by constant a, and add the integral of our function little g of x multiplied by the constant b. So we do not have to do any additional work in calculating integrals which are sums or functions which are sums of other functions. So this property is called linearity of integrals. Now the last property is the following, so that is that if we compute the integral from a to b of a function little f of x, we add the integral from b to c of the same function. Then if you think about areas, then what you get is the same as calculating the result, the integral from a to c of the same function. And that makes sense, because this is the area under the function f between a and b, this is the area between b and c, and we get the same if we compute the area between a and c in one step. Now let us illustrate rule 3 by our functions. To this end, we first have to compute, say, the integral from 0 to 5, if we choose our point a and b equal to 0 and 5, of our function f of x dx. Now, our example function little f of x was 3x, so we get the integral from 0 to 5 of our function 3x. This is equal to the function value of the primitive at 5 minus this function value at 0. Very often in the calculation of integrals, we would write this thing as the primitive evaluated between the points 0 and 5. So this is a very common notation. Now, since we already calculated our primitive, we have to compute the value at 5, so we get 3 over 2 times 5 squared, and we have to subtract the value at 0, and so what we get is 75 over 2. Now, if we had chosen another primitive, for instance, we had chosen not a constant equal to 0, but to 10, then of course this value would have been 10 larger, but this value as well, and so in this subtraction this would disappear. So the resulting expression is independent of the chosen constant c, and the easiest thing to do is of course to take it equal to 0. Now if we compute the same, the integral, or if we compute the integral over the function little g between the same values of little a and little b, then what we get is the following. So we have to calculate the integral of x squared between the values 0 and 5. Now we will write this in this form. So in the standard notation it will be written as the function capital G of x between 0 and 5. So this will be the value at 5. Now what does it mean? It will be 1 over 3 multiplied by 5 to the power 3, and we have to subtract 1 over 3 multiplied by 0 to the power 3, and we get 125 over 3. Now suppose that we take the constant capital A equal to, what do we do, 5, and the constant capital B equal to 6. Then what we get, if we want to compute the integral over the capital A multiplied by the function little f of x plus capital B multiplied by the function little g of x. So if we plug in our example functions f and g, we get the integral from 0 to 5 of our constant 5 multiplied by 3x plus 6 multiplied by x squared. According to the rule, this is 5 times the integral from 0 to 5 of our original function little f of x plus capital B, which is 6 multiplied by the integral from 0 to 5 of our function x squared. And this is 5 times the integral from 0 to 5, which is equal to 75 over 2, plus 6 times the integral that we calculated over here, which is 125 divided by 3. And what we get is, well, 2.5 times 150 is 300. 337.5 if I calculate correctly, plus 2 times 125, and you can calculate the answer yourself.